So in this video, we're going to continue thinking about this, infamous iron bar problem, but we're going to go from thinking about it in terms of a sort of set number of chunks, right? We've certainly thought about what if we make it into one chunk, what if we make it into two chunks, what if we make it into n chunks. And instead we're going to think about an arbitrary chunk, and our intention as we think about an arbitrary chunk is to go from this sort of linear algebra differential equations framing in the direction of a partial differential equation framing of the problem. So the way we're going to think about this is we're going to think about some chunk of the bar, right? And we're not going to talk about how big or small that chunk is, it's just some chunk. We'll say it starts at the point x equals a and it ends at the point x equals b. Okay? Could be a big chunk, could be a little chunk. And what we're interested in asking is how much heat energy is stored inside of this chunk, and how does the heat energy in that chunk change in time? Well, to start with, let's think about the total amount of energy that's stored in the chunk. So total heat energy between A and B. Well, if you think about it, first of all, as I am at different points in this chunk, pretty clearly the temperature is going to change. So I really need to add up what the amount of energy is that's sort of stored in each slice of this chunk. So if I wanted to figure out that total energy, I would say that that was equal to an integral from x equals a to x equals b. And I'd think about how much energy was stored in each slice. Well, stored in each slice, I'm going to have heat capacity times the density times the cross-sectional area, right? This is area times dx, right? That's the volume of the slice. Area times dx is the volume of the slice times the density times the heat capacity, right? Times the temperature at that particular position, right? So I've got an integral from a to b of c times rho times a times the temperature as a function of position dx, right? That's how much energy is stored there. If I ask the question, how fast is that changing, right? If I say, well, what's d by dt of the integral from a to b of c rho a t dx? Well, the only way that the energy in that slice can change is by two processes. One is I can have energy coming in this side, right? And I could also have energy leaving out of that side, and vice versa if I change signs. But it's basically what's the rate of energy flow across this surface and what's the rate of energy flow across this surface. So I'm going to call those things phi sub a and phi sub b, where these are the energy fluxes. This is the flux of energy across surface A, right? In other words, it's the amount of energy per unit time crossing that boundary, right? So I've got some energy that's coming in through this window, and if I define my direction to be to the right, I've got some amount of energy per unit time going out of that window. So if, for example, the amount of energy coming in the left per unit time was the same as the amount of energy going out on the right per unit time, this quantity wouldn't change, right? I could have all kinds of energy flowing through, but I wouldn't actually be raising the temperature at all because I'd have just as much leaving as going in. If I have more stuff coming in than going out, this quantity is going to go up. If I have more stuff going out than coming in, that quantity is going to go down, right? Okay, so now I'm going to apply the sort of fundamental theorem of calculus and look at this. And if I think about that, the difference in the flux that's coming in on the left compared to the flux coming in on the right is actually simply the negative integral from a to b of the derivative with respect to position of the flux, right? That's just fundamental theorem of calculus. So I've now got this expression, right? d by dt of the integral from a to b of c times rho times a times t dx is equal to this thing. Now if I look at this, the only thing that actually depends on time here is position, and so I can actually bring that inside and notice that t actually depends on position and on time, so I'm going to have to actually make that be a partial derivative. So I have integral from a to b of c times rho times a times the partial of t with respect to time dx is equal to minus the integral from a to b of the partial of the flux with respect to position dx. Okay. Well, if I look at these integrals, I have the same limits of integration, right? So it must be the case that this argument is equal to this argument, because of course these limits of integration are arbitrary, right? I can make a be whatever I wanted it to be, I can make b be whatever it wanted it to be, and still it would be the case that the left-hand integral would equal the right-hand integral. So we've gone from an integral statement here to one that we can actually state in a sort of differential way. C times rho times A times the partial of the temperature with respect to time must be equal to minus the partial of the energy flux with respect to position. Now, if I take just a minute to think about what that means, what that means is that if my flux as I move to the right is increasing, right? If d phi by dx is positive, what that means is that as I go further to the right along this bar, I get more and more and more energy flow, right? That's what a positive value of d phi by dx would be. And the only way that I could have more and more energy flow as I went further along the bar is if I was actually losing energy from, like, for example, I think about this point here, I've got more energy leaving that point than is coming into that point. The only way that could happen is if the temperature was actually dropping in time there, right? So this expression that says that the time rate of change of the temperature is proportional to the negative flux of energy really makes sense when the derivative of the flux is positive. That says you're losing stuff out of that position. When the derivative of the flux with regard to position is negative, what that says is that I've got a situation like this where I've got a positive flux here and a slightly smaller positive flux here, so that at this point, let's say I have 4 arrows coming in and 3 arrows going out. Since I have 4 arrows coming in and 3 coming out, I've got more stuff coming in than going out. That suggests that d phi by dx is negative, right? The flux here is lower than is here, so the temperature must be going up because I've got more coming in than going out. Okay? So this is a very general statement about how the temperature changes in time. It just says that it changes in time according to how much flux there is, and in particular not just how much flux there is, but how the flux is changing with respect to position. And in the next video, we'll talk a little bit about how we think about the sort of physical origins of flux and sort of how we also think about flux as a physical quantity.